SwayamPrabha. Digital India. Educated India.
So, the next experiment in the free vibration case is the vibration of a 2 degree of freedom system, and here we have a very simple test setup comprising 2 simple pendulums, but these 2 pendulums are connected through a floppy spring here at these 2 points. These 2 individual pendulums are fulcrumed at the top, so they swing about this hinge, and if you disconnect the spring, then these 2 pendulums are independent pendulums, but this spring is there to connect these 2 pendulums through the connection points at these 2 positions. So, it actually means that you cannot have the motion of these 2 pendulums independent of each other. So, they are all coupled basically, and therefore, this becomes now a 2 degree of freedom system. So, the first degree of freedom is the angular displacement of the first pendulum and that of the second pendulum. The theta 1 of this pendulum and theta 2 of this pendulum are the 2 degrees of freedom for this coupled pendulum 2 degree of freedom system. The connections and so the connection of these 2 pendulums is such that it is constrained to move in the vertical plane. So, the motion is essentially a planar motion, swing about the mean equilibrium position of the pendulum. Now, there would be interesting things to learn from this experiment, and the first thing that we are going to do is the natural modes of vibration for the 2 degree of freedom system. The mode shape, if you all recall, it is possible to show through the theoretical route that the 2 natural frequencies can be obtained based on the dimensions, for example, the length of the pendulum and the stiffness of this particular spring and the position of the connection of the spring from the hinge. All of these parameters will tell you what is the first natural frequency and what is the second natural frequency. In addition to the natural frequency, we all know that there is something called as the mode shape, and it is possible for you to find out that in the first natural mode of vibration, the 2 pendulums will swing in phase. That means, the motion of the 2 pendulums will be in phase, and both the pendulums will move with the same angular displacements, and if this pendulum reaches its peak positive theta value, at the same instant of time this pendulum will also reach its peak angular displacement value, and both of them will move in phase. Okay. So, that is basically is the first natural mode of vibration, and the mode shape here is 1 1. That means, if this swings by 1 unit, this also swings by 1 unit in the same direction. The spring in that particular mode obviously will be inactive. Why? Because the angle turned by this point in the counterclockwise sense will be same as the angle turned by this pendulum at this point. The displacement of this point and the displacement of this point is in the same direction, and which means that there will be no compression or stretch in the spring as the vibratory motion goes on. So, therefore, the spring is inactive in the first mode of vibration, and so this is how the 2 pendulum vibrate or oscillate, and the spring simply moves like a rigid body. In the second mode of vibration, because the 2 pendulum are identical in their dimensions and other details. So, if I displace these pendulums in opposite sense, that means, if I give theta 1 as let us say plus 1 unit and theta 2 as minus 1 unit and then release it, these 2 pendulums will be now swinging back and forth in the second mode of vibration. So, you can see that this one moves by 1 unit, whereas this one moves by minus 1 unit, and then what you observe is the second mode of vibration. So, let me show that to you again. The mode shape in the second mode of vibration is 1 minus 1, which actually means that if I displace this pendulum in the counterclockwise sense by 1 unit angular displacement and this one by minus 1 unit, which means that I am displacing them in opposite direction by the same angle and then release it, the ensuing vibration will happen at the second natural mode. And you can notice that where the two pendulum comes together and they move away from each other, and when this one reaches at its peak positive value, this one will reach at its negative peak value, but both of them will move with the same period of oscillation as you are noticing it. The pendulums will come back to its mean equilibrium position gradually because of the damping provided at the hinges or aerodynamic damping, and therefore the oscillations decay gradually. In contrast to the first mode, when the two pendulums swing together in the same phase, in the second phase or in the second mode of vibration, because they move in opposite direction, the spring comes into action, okay? And therefore, the spring, you can easily see that it is getting stretched and compressed as the movement of the pendulum continues. So, the spring is effective in the second mode of vibration, and whereas it was not effective in the first mode of vibration. Now, we have already learned in a 2 degree of freedom system that if we give the initial displacements to the masses in a way that it matches with the mode shape of that particular system, then the resulting ensuing vibration response as t progresses will happen at that particular natural frequency, which actually means that if the 1 is the mode shape for the first mode of vibration, then if I displace these two pendulums by giving initial displacement as 1 unit for this and 1 unit for this, and then release it at t is equal to 0, since the initial displacements match with the first mode shape, the ensuing vibration response after I release them takes place at the first natural mode of vibration. So, the mode shape is 1 1 and the vibration happens at the first mode natural frequency. If I displace them at t is equal to 0 in a way that it matches with the second natural mode or the second mode shape, that is 1 minus 1, and then release it, the ensuing vibration happens at the second natural frequency, and every time the displacement ratio between this pendulum and this pendulum, they maintain the same displacement ratio which matches with the second mode shape. Now, we have also learned that the general vibration response of a 2 degree of freedom system, when the initial displacements do not match either with the first mode or with the second mode, the general vibration response will have contributions from both first and the second mode, okay? And that we are going to see here. So, what I am going to do is keeping this one at 0. That means I am not displacing the first the second pendulum. The first pendulum I displace it by 1 unit in the sense any arbitrary initial displacement. Now, this of course do not match with either the first mode shape nor with the second mode shape, and when I release this both of them together, then the ensuing vibration response is not pure first harmonic first natural frequency, and nor is it going to happen with the second natural frequency. Now, what you are noticing here is that when I displace initially displace these two masses or two pendulums, not honoring the first mode or second mode shape, then the ensuing vibration response will be through the contribution from the first as well as second mode. Okay. So, what you are observing is you just observe one of the two pendulums, each pendulum is swinging back and forth with a frequency that is not going to be either the first or the second one, and the motions are not harmonic. So, what you are observing that the amplitude keeps on increasing, then it becomes 0, and then it starts picking up again it becomes 0, and this kind of a motion is peculiar here. We call that as a beat motion, and the reason for that will be clear to you. So, I am again going to demonstrate this arbitrary excitation. So, initial conditions are not same as the mode the first mode or second mode, it's different than that. So, what you are observing is a beating phenomena. So, this amplitude picks up and then it becomes 0, yeah, you can see that it is becoming 0, again it will pick up, again it will pick up, and then again it becomes 0. So, the amplitudes are going to increase and decrease in a periodic fashion, and that is the beating phenomena. Whatever that happens at this to this mass, same happens to the other mass as well. Okay. So, let me show you by giving the initial displacement to the second mass. So, now this is how it is going to vibrate. This has come to 0, now it has picked up, again it will become 0, and that is your beating phenomena. Now, we all know that beating happens when the two frequencies are close enough. When two frequencies are close enough, it leads to a beating phenomena. Now, what is happening in the first mode of vibration? The spring was not contributing, so it has certain natural frequency. In the second mode, the spring was contributing. So, the only difference between the first mode and the second mode is the participation of this spring. Now, this spring is too floppy, okay? That means the stiffness is very low, and the fact that it is connected very close to the hinge, the contribution from the spring to the natural frequency is really very small. So, a slight change in the contribution because of the spring stiffness causes the second natural frequency to be slightly more than the first one, and because in the general vibratory response of this 2 degree of freedom system, since we have contribution from both first mode natural frequency and second mode natural frequency, the two frequencies being close to each other results into this kind of a beating phenomena, and the beat period can be now measured here. So, what we are going to do is to use a stopwatch and measure the period between the two zeros, and we will find out from the theoretical expression whether that matches with what we are measuring from the experiment, right. So, first thing we are going to do is to find out the natural frequency of the first mode of vibration by counting the number of oscillations in a given period of time. Do that for the second mode, and then as a general response we are going to disturb this arbitrarily without matching the initial displacements to either of the two mode shapes, and then observe the beating phenomena. We will measure the beat period and then cross check it using the theoretical expressions that we know. So, the rest of the details of the lengths, the spring stiffnesses, everything will be given in the handout which we will upload. So, this demonstration is only to let you understand the 2 degree of freedom system, the mode shapes, and the beat phenomena, which is very peculiar here. So, again look at how the beating happens. Amplitudes comes to 0, again grows up, again becomes 0. That's the kind of beats that you will observe, and whatever happens to this mass or this pendulum happens to this pendulum as well. Okay. Can we get so I'll record the oscillations, and that should give us. Okay. So, let us first measure the period of oscillation in the first mode. So, I am displacing both of them 1 1, and then I will start. So, about 16.7 seconds it took for 10 oscillations. So, about 1.67 seconds is the time period, okay. And let's see 1.67, you can note it down, and then we will see as to how this one changes when we excite it in the second mode. So, yeah, here it is. 14.4 now it shows, 14.4. I will do it again. So, I think 1.42 is the period in the second mode, and obviously it has to be smaller than the first one, because we are looking at the second natural frequency, which is going to be slightly more than the first one. Okay. Now, let us record the beating period. So, 8.36 is the period between two stationary positions, okay, and then that can be translated. There is a expression that helps you to find out the beat frequency. Okay. So, 8.36 is the time between the two successive 0 positions, okay, or 0 amplitude positions.